Okay, great. So now we're going to talk about Bronsted Lowry acid-base theory really quickly. This again is review. I totally get it. I cannot emphasize how important it is that you understand Bronsted Lowry acid-base theory. It is essentially the acid-base theory. There's other ones, but this is the one that we use on a daily basis. Okay. So Bronsted Lowry, what they did was they looked at acid-base reaction, and they first of all said that what happens in an acid-base reaction is that the base takes a hydrogen away from the acid. So essentially the acid transfers one of its hydrogens as a hydrogen plus with no electrons, transfers that to the base, or the way I prefer to think of it is the base grabs one of those hydrogens from the acid. Okay. So the acid donates a hydrogen and the base accepts it. The base makes a bond. But what they did, I think that was so groundbreaking was they realized that if we look at the overall process, then at the end of this process, on the other side of the equilibrium equation, the products are also acids and bases. Because in the reverse direction, what we see then is that this species here, to get back to where it started, it's going to grab a hydrogen, which means it's going to be a base. And this species here, to get back, it's going to give away a hydrogen, which means it's going to be an acid. So what you had was you had an acid, excuse me, I can spell, on one side, and then that acid would have a related base. And instead of using the word related, which is what I would have used, they used conjugate. And I guess that it implies sort of this reciprocal, conjugate implies this reciprocal relationship. Okay. So they're related in sort of a reciprocal way. Okay. The point being that I'm sorry, I wrote the wrong thing. It's conjugate base. Right? An acid forms a related base, and then a base forms a related acid. And again, there's this reciprocal relationship. Okay. I want to point out, however, that a conjugate base is just a base. It's only conjugate in the context of this equilibrium reaction. If we put it in a different reaction, it could be on the left-hand side of the equation and just be the base. Does that make sense? So don't get confused about that. All it's really saying is that in this reaction, as we have it written, there's this reciprocal relationship. And the things on the right-hand side, we're going to say, are the conjugates of the left-hand side. All right. So the other thing was the idea of this equilibrium. Okay. And one of the things that, I mean, there was a lot of stuff being developed about equilibrium theory, and it had been really well developed by this time. But the idea of this is that while we're used to sometimes thinking of this reacts with that, boom, done. In reality, especially in acid-base reactions, yeah, an acid will react with a base, but then since it forms an acid and base on the other side, those can react and go backwards. And so typically a couple things, typically we don't get necessarily 100% of the stuff is on the reactants or 100 stuff on the products. We get an equilibrium mixture. Certain percentage is still reactants, certain percentage will be products, okay? So that is actually super important also. Alrighty, so then in first semester, we went in detail about pKa's. I'm not going to go through all that math, but basically the pKa is a measure of how strong an acid is. It's a measure of the equilibrium constant of the reaction of the acid with water. Okay. And the main thing is that as the acid becomes stronger, the pKa, which is minus the log of the equilibrium constant, becomes larger, more negative. And then there's a table. And I'm not going to make you memorize this table. It will be provided for you on every exam if we have exams. You're welcome to refer to it. I don't make my students memorize this table. Even in person, I provide it. But basically what we see is on the left-hand side, we see these are different acids. A lot of them will look familiar. On the right-hand side, these are the conjugate, the related bases. It's what you get if you take away one hydrogen and a positive charge. And the number here is the pKa of this acid, but we're also going to talk about how this base relates to that pKa number. We're going to call this the related pKa of the base. We also see that the strongest acids are listed on the top of this table where the numbers are most negative. The numbers go up to 0 and then they go to positive. And finally, a strong acid has a weak base. A weak acid has a strong base. There's this reciprocal relationship. And so we have strongest to weakest on this side. On the right-hand side, we have weakest base going to strongest base. So here they all are. We can use this to calculate K equilibrium. We're going to do that in our first lecture. K equilibrium can be estimated by just looking up the pKa of the acid on the product side and subtracting the pKa of the acid on the reactant side. So it's products minus reactants. And then I just generally leave that in the exponential format, 10 to whatever that number is. You're going to see that in the lecture. Finally then, I just want to review chapter 8. There's a couple reasons. We sort of rushed through chapter 8, so it's something you may want to look at again. But also, we're going to be building on double bond reactions from chapter 8, from the very beginning. Okay? And so, one way that we look at these double bond reactions is we look at the reagents that react with the double bond and we say that reagent can be broken into an electrophile, which is something with a positive charge. It's attracted to electrons. The pi bond has a lot of electrons, so it's attracted to the pi bond. And then once it reacts, it creates an empty space for a nucleophile to make a bond. So that what often happens in a sizable number of our reactions is that the double bond sort of absorbs that pair of species, okay? And in the product, the double bond is gone because it was used to make a bond. And the resulting product has extra atoms in it. And so we call this an addition reaction because we're adding stuff to the formula. There's a general mechanism for this. Quite frankly, most of our reactions, when we actually looked at them, they didn't follow this exact general mechanism, but it's useful. In the first step, the positive charge attracts a pair of electrons. So you see the electrons start here on one of these bonds, they move and they make a bond to the electrophile. So this does two things. So now there's only a single bond here because we used that bond. That bond is going to be somewhere attached to one of these carbons, and then it's going to have an electrophile on the other end. The electrophile probably doesn't have its charge anymore. But then that leaves this other carbon with only 3 bonds, and when a carbon has only 3 bonds, it gains a positive formal charge. So now that creates an opening for a nucleophile. Nucleophile has a lone pair or a pi bond, has electrons that it can use to make a bond to something with a positive charge. So the nucleophile, this pair of electrons, is attracted to that positive charge and basically moves into the empty space and creates a second bond. So that's how we get our overall structure. And this was written as two separate steps. And in fact, our textbook generally or very often breaks mechanisms down into individual steps on each line. And that's one way to do it. And some people find that easier to see. I prefer to write them as sort of an assembly line process where all the steps are just written sequentially on one in line, on one line, or sometimes you have to go to kind of loop it around, but basically all in sequence. So that the product right here, here's our first reactant, we have a reagent, we have a product. So the product of that first step, we don't have to rewrite it. We just put another arrow and say that product continues on to do another reaction like this. So we basically get a reaction arrow for every step or elementary reaction. No, that's not an H, that's an E in our mechanism. Okay. So again, this is not really anything new. I'm just reminding you of how that works. Okay. And so we're almost done because I'm running out of time here. So if we look at hydrogen halide addition, this is sort of our, in many ways, our very simplest addition reaction. It's super useful. It was one of the first ones that was really studied. It's basically the one that Markovnikov studied. So that hydrogen is going to have a positive charge. Because the chlorine is so electronegative, it's pulling electrons away from it, right? And so now this pair of electrons would be attracted to that positive charge. And again, it makes a bond to the hydrogen. The hydrogen can only have one bond, so it lets go of the bond on the other side. So that pair of electrons has to go somewhere. It goes onto the chlorine. So we get this. That's a carbocation. And then the byproduct of that first step is the chloride ion. Well, the chloride ion, it turns out, is a nucleophile. So the chloride ion can come in and make a bond to that positive charge. And so that's how that works. We're going to use that reaction in an upcoming chapter. Another important one of these is the acid catalyzed hydration reaction. In this reaction, we're not going to worry so much about what acid we're using. What we're using here is we're using dilute H2SO4. It turns out dilute H2SO4 is basically, if we look at it, it's a solution, okay? It's got hydronium, HSO4 minus, and water all mixed together because sulfuric acid reacts with water and it does acid-base reaction. And it turns out that's a favored process. So most of the sulfuric acid is destroyed. It's converted to hydrogen sulfate and hydronium. So technically, our acid here is most likely going to be hydronium. But I just think it's easier not to worry about what the specific acid is and instead to just say, we know we have an acid. An acid is a hydrogen attached to a base. Then in this case, our nucleophile is actually one of the waters of molecule that's part of our dilute solvent system, right? And it makes a bond. And so the whole thing connects. So you see, here's the oxygen, still the two hydrogens, but one of these lone pairs is now a bond. So that oxygen now has 3 bonds in one lone pair. That gives it a positive formal charge. And then finally, it would like to become non-charged. It can do that by essentially giving away a hydrogen plus to a base. So the base grabs a hydrogen plus, pair of electrons goes down, and that creates our product. So these are all things that we're going to see, elements that we're going to see in other mechanisms in upcoming chapters. And finally, I just want to remind you, I'm not going to do the mechanism of this, but we also had a reaction where if we took a double bond, we could treat it with something like Br2, and the double bond would essentially absorb the 2 bromines and make this. This is called a vicinal dihalide. And the reason for that, I just want you to, okay, vicino is Italian for neighbor. So they're saying dihalides that are neighbors. In other words, they're on 2 adjacent carbons. Vicinal dihalides. So you can remember that always if you just remember vicino is Italian for neighbor. So vicino.